Hi everyone, I'm Gabi Ciubotaru. I'm a software developer with a great interest in security, in reverse engineering, embedded system, and also recently in electronics. And today I want to present you my journey while modifying a coffee machine. So, earlier this year, I bought myself a coffee machine, and while it was pretty good, there was a feature that annoyed me. So the coffee machine turned itself off after 30 minutes, and on every power on and power off cycle, it uses a lot of water for the rinsing. So I decided that I need to fix this. And looking into the user manual, I found that I could change the default timeout to 3 hours, but this was not enough for me because I usually took like 4 hours between my coffees. So I decided to fix this timer and yeah, change it for to fit my needs. The approach, initially was simple. What I had to do was to disassemble the machine, find a way to interact with the hardware inside, extract the firmware from the machine, analyze it, find where those settings are stored, and then modifying it and upload back the software. So, first thing, I have opened the main cover and I found this main integrated circuit. Looking at the series, I found it was a PIC-18, a microcontroller that controlled the entire machine. It controlled the sensor, all the motors inside, the heaters, and so on. And yeah, the other ICs were just for controlling, so I knew this is the one that I need to tamper with. And I took the data sheet for it, looking for the pins, see how this should be flashed, and I found that this can be flashed using this ICSP protocol in circuit serial programming protocol. This is a proprietary protocol from Microchip. And here, if you can see, I found some connectors, and using my multimeter, I probe this connector and see where they lead on the main IC. And I found this connector was for power, VCC and ground, and then memory clear, which puts the IC into a into a programming mode, and then the programming clock and data. And yeah, and then I just solder some wires on this, plug the programmer, turn everything on, and boom. My laptop, my docking station, monitor, everything was burned. Because when I soldered these wires, some of the solder slipped on the other contact and make a short circuit. And luckily, my laptop was still in warranty. Yeah, it was easily fixed. Then I had to buy another monitor and everything else, another programmer, and then I decided I don't need to, I shouldn't solder the wires directly on this, and I need to take it out. So on my second try, I took everything out. You can see here, I have the main board that is controlling the circuit. This is the programmer that I soldered on the board. And then I also have extracted the main interaction board. This board had the input buttons and the LEDs that were yeah, displaying different errors or different things on the machine. So after doing this, using the programmer from the microchip, I was able to extract the entire firmware, and then the fun begins. I thought this would be a pretty easy task because yeah, it's a coffee machine, has a bunch of features, but then I realized the code had a few thousand lines, And I was really impressed by this. I was expecting somewhere around a few hundred. Then I'm usually doing the reverse engineering, and usually I'm guiding by strings. But in this case, there was no strings, no debugging. You don't have like a debugging port to see what is happening. There was no error messages in the code, so you can figure out what different pieces are made for. So that was a big, big challenge. And another one was the complex input and output operation. Because usually in embedded system, you want to optimize as much as possible the input and the output and multiplex them together. So you make the entire system cheaper, because for example, instead of using 7 wires, you could use 3 wires and do some optimization there, and you can process this in the code. All right, so being lost in the all this assembly, I found myself, I had to try and find another way to find the actual setting. And then I realized that in the user manual, there was described a settings, and you could choose the timeout for the power off. And it was from 15 minutes to 3 hours. And I said, okay, maybe if I will trace this setting, I can find the actual logic that is controlling the entire power off setting. And then the first thing was to take the input board and see exactly how this is made. And you can see here, this was the connector that was plugged to the main IC. And then here are some buttons, and here some LEDs, and then some shift register and the mutex. So basically, this was controlling the entire input and output operation. So I had to reverse engineering the entire PCB using a scope. And I made the schematics out of it, and I learned how the input and output works on this. So here I have a simple draft on what was happening with the LEDs. So basically here you can see these are the 3 ports that were controlling this shift register. And using these 3 ports, you can serialize a byte value into this shift register here. And then using this shift register, you drive the LEDs. If you can see, the LEDs are, these are the LEDs here, and they are arranged in 2 columns and multiple rows, 4 rows. And then each one of the 0 to D3, these bits were controlling which line is on, and then with the D6 and D7 controlling the rows, the columns, sorry. And finding out this, I could identify that there was this RC5, RC3, and RC4, these IC pins that were used to control the input and the output from the controller. Then, having this knowledge, it was easy to identify the piece of the code that was actually controlling the LEDs. So if you can see here, this code here is, for example, is testing the 7th bit, and then based on this is setting the RC3 or clearing it, and then send this data by sending a clock pulse on RC4, and then moving to 6th bit. And this way, the data here in the RAM 37 was shifted out to the shift register driving the LED status. And having this logic in front of me, I could easily identify which bit represent which of the LEDs. After that, I took the user manual. See, for example, in here for 2 hours, you had the echo, the tray, the water, and the warning sign on. And I looked through the code to see where exactly I can find those patterns. And for example, here, I could find the pattern for 3 hours. So here for 3 hours, the echo, tray, water, warning, and temperature LED were set. And here for 2 hours, only this LED were set. So finding this, I could find that this value here is actually controlling the level. So if you think about it, like this is the level 0, 1, 2, 3, 4, then this variable controls the level, and then based on this level, the actual settings was displayed on the board. And then what I could do is just to trace this variable to see where it came from. And digging deeper into the code, I found this piece of code that was reading from the memory at a specific address. So here you have a value, and this value is multiplied by 2. Then 26 is added to that value, moved into a lower memory addressing register, and then a 6 in the higher part. Oh, sorry about that. And 6 in the higher part. Laser pointer. Okay. And here is the actual formula. So we have a value multiplied by 2, and then an offset is added to that value. And that pointed to an area here in the flash data. If you can see here, 6 to 6. This was the actual mapping in the flash area, and there was multiplied by 2 because every entry in this mapping has 2 bytes, and I could see those values, which were mapped one-to-one to the default settings for the power off. These are not actually one-to-one because 90 is not 90 seconds, but these are these are multiplied by 10 seconds when the timer is set. So basically, these are 900 seconds, which is 15 minutes. And yeah, from now on, after I found this mapping here, I could just change the bytes in this mapping, putting some new values here for like 5 hours, 5 hours converted in minutes, divided by 10, because there is 10 seconds, and change this value here. And then the rest of the thing was pretty simple. You change the binary, you recompiled, not recompiled. I had to transform the binary into a hex file and then upload it on the machine. And then after that, I realized that I need to wait for 5 hours to see if the change actually works. So I changed it again and put the first value to a few seconds just to understand that. After that, when I press the power button, it entering the start procedure, but then immediately it was timing out and turning off. And I said, okay, it's working. And yeah, this is how I managed to save myself like 30 seconds every day with the cost of over 100 hours invested in all this research. But it's totally worth it because now the machine works my way. All right. Thank you so much. Thank you so much, and now I'm open to questions.
Okay, thank you for the presentation, first and foremost. And second, I want to ask a question about how you got into this kind of hobby, to disassemble stuff, to engineer your own software on such machines and stuff like this. What kind of resources did you manage to find to learn this stuff, which seems to me quite amazing?
Okay, so I had a passion for electronics since I was a little kid. And then I worked for Bitdefender, where I did a lot of research, reverse engineering on binaries. And there I learned to do this, reverse engineering. And then recently, in like the last 4 years, I started doing research on embedded system, on microprocessor, learning different architectures, and yeah, powering it up and stuff like that.
Oh, that sounds amazing. Thank you for answering.
Yeah. Thank you so much.
So I wish to ask you about what was the initial knowledge of understand which type of microprocessor is used in that motherboard. So did you find the real integrated circuit which is used there, or do you suppose that could be some of those you are familiar of?
So the question is, how did I found what kind of processor is and how to interact with it?
Yes.
Basically, by looking, yeah, let me go back a little. So looking here on this IC, you can find its serial number, and by its serial number, like it's PIC 18 something, you can search online for the data sheet, and in that data sheet, you can find all the information related to this integrated circuit, like all the pins, what they are meaning, like the architecture inside, like the reset vector, like how the memory is managed, organized, and what are the different instructions that are understood
So you
by.
have a bit of luck there. Do you have a lucky one there? Because usually, mainly in the Chinese product, those codes are not encrypted there. It's not written there. So you don't have the knowledge which one of which type of microprocessor is integrating there.
Yeah, yeah.
Thank you.
Yeah.
Presentation. Thanks. I had like two questions, if I can ask them. The first one is regarding the tools that you use to reverse the binary, and can you tell us what you used? Just
I
curious.
have used DIDA.
Okay.
For
And
disassembling.
did you use the same tool to patch the binary, or with the value,
Yeah, I
or
patch it manually.
manually?
Like
Or
you can do it
you
with
just looked at
Python
it?
code, or you can do it in a hex editor like HXD.
All right, yeah. And my second question was, I suppose you also tried this on other devices, or you reverse them, I guess? Yeah. Well, I also started to have this passion, and I was wondering, what do you do if you find a processor that had, like an ESP32 that's technically encrypted? What would you do in that case?
If it's encrypted.
Yeah.
Yeah. All right. So basically, when you have a microprocessor that uses encrypted data, you usually target the update system. Because during the update system, somewhere on the line, that package needs to be decrypted. And this is where I've done this in the past, and this is how I extracted the firmware.
Oh.
Not from the chip itself, but
from
I
the-
have exploited the upload procedure.
Oh, okay. That's a nice idea. Thanks.
Yeah. Sure.
Hi, thanks for the presentation. I was wondering if it's possible to find this kind of exploits without actually opening the coffee machine. I mean, you open it once, okay, but is it possible to find like a sequence of buttons that you can press and maybe activate some hidden settings or some service menu or something like that, and then publish these findings on the internet?
Yeah, I'm sure you can find vulnerabilities and exploits into the pressing buttons and overwriting the code and do stuff like this, but that's pretty hard. I don't think it was the effort, to be honest. And usually when you have this kind of machines, you usually you're targeting the input, like if you have a Bluetooth or Wi-Fi that where you can inject more data, not the button, because it's pretty hard to get something corrupted just by buttons, and it's pretty complex.
Yeah, the idea behind it is maybe I don't want to open my coffee machine because I don't want to lose the warranty. But if somebody else finds the exploit and prints the list of the buttons that you need to press on somewhere on the internet, then I can do this safely in my home.
Yeah, I'm sure you can find something like that. So if you know in the Mario system, in the NES system games, inside the Mario game, you could reprogram the entire world just by pressing the buttons on the controller. Somebody found an exploit that could rewrite some of the assembly, but this is pretty tedious.
Thank you.
Yeah.
First of all, thanks for the presentation. And I wanted to ask, did you think about another approach? For example, if I were to do something like this, I think I'd rather use another board to control the main board, such as an Arduino with extra buttons that would control the buttons of the coffee machine instead of rewriting the firmware. And if you thought about other approaches, why did you choose this one?
Yeah, I was thinking about this too, to put a module that has Wi-Fi and replace the entire this part by that module, so I can interact with the coffee. But to be honest, I like doing reverse engineering, not this kind of stuff.
So it's a personal
Yeah,
preference.
it was like a challenge. Yeah, I took it as a challenge if I can do that.
Thank you.
So my main question was, did tampering with the coffee machine affect in any way the lifespan of it?
Sorry, can you?
So, did tampering with the coffee machine
Okay.
and changing the firmware affect in any way the lifespan over the years, or?
Yeah, it shouldn't affect as long. The only thing that is coming to my mind right now is that it will stay on for longer period of times. I guess this is the only side effect. But in terms of code, it should be the same.
Ah, okay. Thank you.
Yeah. Thanks. Any other questions?
Thanks for the presentation. Have you found any other functions in the firmware, like the function for the receipt? Have you tried to modify it, maybe, making the timer for the milk longer?
Yeah, I have found a lot of settings. So after I have finished this targeted reverse, then I looked around that piece of code and I found a lot of settings in the nearby of the code that controls the timeout. So yeah, I could find the heater settings, the rinsing settings, the water pump and all of this. So yeah, I could change all of these parameters within the code.
Thanks.
Yeah.
Yeah, thanks again. I have one more question for, let's say, the beginners or the people who want to get into this. What would you recommend them to do as a first step or first target, or yeah? I don't know.
The first thing to do,
Yeah.
play around with Arduino, with Raspberry Pi, and then start with chips like ESP32, or try doing it on a smart light bulb on SmartThings that already has a debugging port, so you can easily interact with them.
Okay.
Yeah, so I guess this would be some first
Yeah.
steps.
Thanks.
another question. Let's say if they wanted to, could they, let's say, encrypt everything, like encrypt the ESP, encrypt the bootloader, encrypt stuff like that, so this kind of exploit would not be possible?
Yeah, you can encrypt everything, but this brings cost. So you don't want to add cost to this kind of machines because you're selling millions of them, and every chain added to one machine is multiplied by 1 million. So you don't want to do that.
Makes sense. Thank you.
By risking your entire firmware to be collected and reversed, you don't. Yeah, usually you can't afford to pay that much money. Yeah.
I wanted to ask how difficult would have been to wire a different logic to this existing machine in order to add some extra sensors, like shutting down the machine or put it into sleep if the light went off.
Yeah, I guess you can rewrite the entire firmware, implement your own logic, find out some logic that you don't need and wipe it out and skip for some safety check. There was a lot of safety check for the temperature sensor, for example, if in case of overheating, you would cut the current. So you could wipe out some of this code and put it.
Okay, but is it more difficult to change the logic inside this chip, or maybe add something different to it and just wire the connection?
Either way, I guess as long as you have the chip, you can reprogram the entire firmware. You don't have to keep
do
it
anything you
anything.
want.
Yeah.
Okay.
Yeah, you can start it from scratch and create your own initialization, memory management, and stuff like this, and you can write your own code.
Okay, thanks.
Okay, any other question? Okay, thank you so much for your attention.